In this unit 2, we are going to discuss these topics under infrared spectroscopy. And today's video lecture is going to be on vibrations of simple harmonic oscillator and zero-point energy. Infrared spectroscopy is a chemical analysis technique that measures the interaction of infrared radiation with matter to identify and analyze chemical substances. Infrared spectroscopy uses an infrared spectrometer to measure how a sample absorbs, emits, or reflects infrared radiation. IR spectroscopy can be used to identify and quantify chemical substances in solids, liquids, or gaseous samples. It is used in a variety of applications including forensic analysis, quality control, environmental monitoring, studying catalysts, comparing samples, and so on. IR spectroscopy is based on the idea that a molecule's vibrational and rotational states can be altered by electromagnetic radiation. The absorption of radiation occurs when the frequency of the radiation matches with the natural vibration of the molecule. We are going to introduce the infrared spectroscopy. We know that a diatomic molecule leads to rotational spectra due to the elasticity of chemical bond. In addition, these bond stretches under centrifugal forces. Another consequence of the elasticity of the bond is vibration of atoms in a molecule about its mean position. Thus, the molecule undergoes vibration and rotation simultaneously. It is observed that the vibration energy has larger energy level spacing after the rotation energy of molecules. The transition between the vibration levels gives the vibrational spectrum of a molecule. The energy of the molecular vibrations is quantized, corresponding to the infrared region of electromagnetic spectrum. So this is the electromagnetic spectrum, and in the unit 1, we discussed the rotational motion, which is studied under microwave spectrum or rotational spectra. But in this unit, we are going to cover infrared radiation, and this is about molecular vibrations. And look at the energy. Energy is greater than that of rotational motion. So energy of the vibration is greater than that of energy of the rotational motion. When infrared radiation of the same frequency is allowed to fall on the molecule, then the system absorbs energy. It causes the excitation of a molecule to higher vibration energy levels. The absorption of energy gives rise to bands falling around 200 to 4000 cm/-1. The infrared region covers the range from 50 to 12,500 cm/-1 approximately. It is divided into 3 regions: near infrared 12,500 to 4,000 cm/-1, middle infrared 4,000 to 400 cm/-1, and far infrared 400 to 50 cm/-1. The middle infrared is the most commonly used for laboratory investigations since it covers the most of the vibrational transitions. However, the far infrared region deals with the solid samples. Once the vibrational frequencies are obtained, the valuable information regarding the molecular structure, symmetry, bond length, intermolecular interactions, and so on can be derived. The infrared region, just below red in the visible region in the electromagnetic spectrum, and wavelengths of infrared region lie usually 2.5 to 25 nanometer. More common units are wave numbers. The unit of wave number is nothing but centimeter/-1, which are proportional to frequency and energy. The reciprocal of the wavelength in centimeter is 4000 to 400 centimeter power minus 1. Infrared active bonds. All covalent bonds will not display bands in the IR spectrum. Only polar bonds alone will display IR spectrum. They are referred as IR active. The intensity of the bands depends on the magnitude of the dipole moment associated with the bond. Stronger polar bonds, such as carbonyl groups, produce strong bands. Medium polarity bonds and asymmetric bonds produce medium bands. Weakly polar bond and symmetric bonds produce weak or non-absorbable bands. Infrared radiation is largely thermal energy. It induces strong molecular vibrations in covalent bonds, which can be viewed as springs attached with two masses or two atoms, which are depicted in the figure. Specific bonds respond to, or which is nothing but absorb, specific frequencies. And in a diatomic molecule, we have two atoms. It's like attached with a spring. We can visualize. And this is our equilibrium bond length. We can stretch and we can compress. And it makes a linear harmonic oscillator. So this is nothing but vibration. IR bands can be classified as strong, medium, and weak depending on their relative intensities in the infrared spectrum. A strong band covers most of the y-axis. The medium band, so strong band covers most of the y-axis. Medium band falls to about half of the y-axis, and a weak band falls about 1/3 or less than that of y-axis. So let us come to the topic of this unit. Vibrations of simple harmonic oscillator. Here, each atom is connected to the molecules with a bond acting like a spring, and it undergoes a harmonic oscillation about its equilibrium position, stretching and compressing, or extension and compression. All atoms move in phase with the same frequency. The vibrating diatomic molecule is a simple harmonic oscillator model. Atoms in molecules execute vibratory motion along with bond length and bond angle, which changes periodically, is called simple harmonic motion. A body that executes simple harmonic oscillation or a motion is called a harmonic oscillator. Here, chlorine is heavier. For example, when you take HCl, chlorine is heavier, and this hydrogen bond, which is attached with the chlorine, that can oscillate. It can compress and it can extend. Compress and extend. Stretch and extend. Suppose if vibration is more, then we'll have more compression and more extension. It goes on. And we are going to draw the graph between E versus internuclear distance. And this point is nothing but mean position, which is nothing but R equilibrium. In a diatomic molecule, the balancing of forces arises because there is a repulsion between the positively charged nuclei of both atoms and between their negative electron clouds. On the other hand, there is an attraction between the nucleus of one atom and the electrons of the other, and vice versa. The two atoms have a mean distance such that these forces are just balanced, and the total energy of the whole system is a minimum. Squeezing the atoms more closely together will cause the repulsive force, whereas the pulling them apart is resisted by the attractive force. The energy as a function of internuclear distance of a diatomic molecule, for example HCl, has been plotted in the figure, which you are going to see now. Here the chlorine atom is kept on one axis, and imagine pushing and pulling of the hydrogen atom closer to chlorine atom will set the change in energy. So stretch and expand will result a change in energy. So this is the example. So we have hydrogen chloride. Cl is heavier than that of hydrogen. So Cl is fixed and hydrogen moves back and forth. So compression and extension, stretching and extension. So we have now this point E2. So E2, look at E2. The energy is produced due to the change in compression and the extension. And of course, when it moves faster and moves extension, this will have more energy. So E1 is greater than that of E2. And the energy as a function of internuclear distance of a diatomic molecule is shown in the figure. In the figure, we have plotted the energy in the form of equation 2.2. This is as a parabola. So 2.2 is written here. This is E equals 1 by 2 half R minus R cube whole square. So this is exactly like half kx squared, which is nothing but a parabolic form. Any energy greater than E2 arises due to the extension or compression of the bond. The figure shows that if one atom, chlorine, is considered to be stationary at R equal to 0 axis, the other atom, hydrogen, will oscillate between H prime and H double prime. In the case of HCl, the heavy chlorine atom stays virtually still, and it is the lighter hydrogen atom which moves back and forth about its main position during the vibrations. Thus, the distance between the two atoms is important in the system. One can imagine that one atom is stationary and the other atom is moving back and forth, and thus diagram can be applied for any diatomic molecule. At the energy minimum, the internuclear distance is referred as the equilibrium distance, which we call this as REQ, or more simply as the bond length. So equilibrium distance is nothing but the bond length, the mean distance between two atoms in a diatomic molecule. The compression and the extension of a bond is similar to the behavior of a spring obeying law, F equal to minus Kx. So here it is F equals minus K R minus RQ, where F is the restoring force, K is the force constant, R is the internuclear distance. The energy curve is parabolic and has the form as E equals 1 by 2 Kx squared. So 1 by 2 K R minus RQ whole squared. This model of a vibrating diatomic molecule is called as simple harmonic oscillator model. With some approximations, one can explain the vibrational spectra easily. If the energy of the HCl molecule of figure is increased to E1, then the oscillation will become more vigorous. The compression and the extension will be greater, but the vibrational frequency will not change. It will be always constant. An elastic bond, like a spring, has a certain intrinsic vibration frequency which will not change. An elastic bond, like a spring, has a certain intrinsic vibration frequency, depends on the mass of the system and the force constant, and the oscillation frequency is given by omega, which is equal to 1 by 2 pi root of K by mu. It is measured in terms of H, where mu is the reduced mass of the system, and of course K is the force constant. To convert this frequency into wave number, we will have to divide by the velocity of light. So 1 divided by 2 pi c root of K by mu. Now it is measured in terms of centimeter power minus 1. Here omega bar, omega oscillation bar, this is nothing but due to vibration. And in the last minute, we studied about the rotational energy. That was measured in terms of nu bar. Here it is omega bar. This is for vibration and that is for rotation. This is the unit centimeter power minus 1, which is most usually employed in vibrational spectroscopy. Molecular energies are quantized, and the allowed vibration energies for any particular system may be calculated using Schrödinger wave equation. For the simple harmonic oscillator, the expression for the energy is given by, we know already this expression, E nu, which is equal to nu plus 1 by 2 h bar omega. it is measured in terms of joules, where nu is the vibrational quantum number. So it's a number, and it goes from 0, 1, 2, 3. Converting to the spectroscopic units, which is in terms of centimeter power minus 1, we have the expression for the wave number as E nu, which is equal to E nu divided by Hc, which is equal to nu plus 1 by 2 omega bar. So now this is measured in terms of centimeter minus 1, and this is known as wave number. So this is known as wave number for the vibrational frequency. So these are all the allowed energy values of a simple harmonic vibrator. Some of these energy values are shown in the figure. So these are the values which are shown here, and when you are going to substitute for nu, it's a vibrational quantum number. So nu equals 0, substitute here in this expression. We will get 1 by 2 h bar omega. Suppose if nu equals 1, we will get E1 as 3 by 2 h bar omega. Substitute nu equals 2, we will get 5 by 2 h bar omega. And difference between these two will give us always h bar omega. And very important thing is the energy levels are equally spaced. So these are the allowed values, and which is these are all the allowed energy values of a simple harmonic vibrator. Some of these energy values are shown in figure. It is noticed that the lowest vibration energy is obtained by putting nu equals 0 in equation 2.5. So this is equation 2.5 and 2.6. So 2.6, and it is given by. So this is expressed in terms of energy, and this is expressed in terms of wave number. So which is measured in centimeter power minus 1. So we have already explained the figure. It implies that the diatomic molecule can never have zero vibration energy. So there will be no zero value. The atoms in a molecule can never be completely at rest relative to each other. The quantity 1 by 2 h bar omega or 1 by 2 omega bar is known as 0 point energy. That is, the vibration energy is not zero even at the lowest vibration level, indicating that the molecule must vibrate always. It depends only on the classical vibration frequency, and hence equation 2.7. So this is equation 2.7 and this is equation 2.8. They refer the strength of the chemical bond and the atomic masses. The spacing between the adjacent levels is del E equals h bar omega. The prediction of 0 point energy is the basic difference between the wave mechanical and the classical approaches to molecular vibration. There is no vibration energy as per classical mechanics, but quantum mechanics insists that it must always vibrate to some extent, and it has been brought out by many experiments. Only those vibrational transitions in which the vibrational quantum number nu changes by 1 unit are allowed. For an allowed transition, the selection rule is del nu plus or minus 1. Since the vibrational levels are equally spaced, any transition between two neighboring vibrational levels correspond to the same energy change. Only one absorption line will be obtained in the vibration spectrum of a diatomic molecule. The changes of vibration energy give rise to an observable spectrum if the vibration can interact with the radiation, if the vibration involves a change in the dipole moment of the molecule. However, the vibration spectra will be observable only in the heteronuclear diatomic molecules, since homonuclear molecules have no permanent dipole moment. Applying the selection rule for the transition from nu to nu plus 1, and we are going to use this formula, and instead of nu, you substitute nu plus 1 in this equation. So the wave number nu plus 1 to nu, so just to substitute, instead of nu, substitute nu plus 1. So nu plus 1 plus 1 by 2 omega bar minus nu plus 1 by 2 omega. So this is for nu and this is for nu plus 1. And of course, this nu and this nu will cancel. So we have 3 by 2 minus 1 by 2 will give us 1. So the wave number between nu plus 1 and nu will give us omega bar, which is measured in terms of 10 to the power minus 1. And this is for emission. Suppose the transition from nu to nu plus 1, this is for absorption. Since the vibrational levels are equally spaced, transition between any two neighboring states will give rise to the same energy changes. Since the difference between energy levels is expressed in centimeter power minus 1, and it gives the wave number of the spectral line absorbed or emitted, which is nothing but omega. This is exactly equivalent expression of absorption or emission in classical terms. In absorption, the vibrating molecules will absorb energy only from radiation once it interacts with the electromagnetic radiation, and this must be the radiation of its own oscillation frequency. Now let us solve one problem. The HCl, hydrogen Cl35, equilibrium bond length is given as 0.127 nanometer, and nu equals 0 to nu equal to 1 transition is observed in the infrared at 2886 centimeter power minus 1. So we are going to compute the vibration energy of HCl in its lowest state, that is nu equals 0. Compute the classical limit for the stretching of HCl bond from its equilibrium length in this state. What percentage of the equilibrium bond length is this extension? So first let us solve to obtain the lowest state energy. So given that the HCl bond is given as 0.127 nanometer, which is nothing but 1.27 in 10 power minus 10 meter, and it is observed as 2880 centimeter power minus 1. First we will convert this wave number into Hertz. We know that C equals nu lambda and C by lambda equals nu. 1 by lambda is nothing but nu bar, wave number. So nu bar multiplied by C, that will give us nu. So 2886 multiplied by 3 in 10 power 10, that will give us 8.646 in 10 power 13 Hertz. The equation for the nu eigenstate of the harmonic oscillator is given as A nu, which is equal to nu plus 1 by 2 h bar omega, where nu is the vibrational quantum number. And we know that omega equal to 2 pi nu, which is given as 5.54 into 10 power 14 radians per second. And of course, nu is given. So we have already calculated nu, 8.646 in 10 power 13 multiplied by 2 pi will give us 5.54 in 10 power 14 radians per second, which is nothing but Hertz. Now, so the ground state nu equals 0 energy, and of course E naught equals nu plus half h bar omega. Putting now nu equals 0 will give us E naught equal to 1 by 2 h bar omega, and substitute the corresponding values. H bar equal to h divided by 2 pi. H is nothing but 6.626 in 10 power minus 34 divided by 2 pi, that will give you h bar. You substitute, we will get 1.0551 in 10 power minus 34 times omega. Just now we have calculated, which is given as 5.54 in 10 power 14, and we will get the E naught value as 2.923 in 10 power minus 20 joules. The classical limit of the stretch is denoted as x. So this is the energy. This is nothing but the lowest energy. The classical limit of the stretch is denoted as x. This can be equated as potential energy in the relation to total E naught found above. Start E naught. All of the energy would be potential energy in the form of stretch. So in the form of stretch, all the energy will be converted into potential energy. So in comparison to the classic spring potential, we know that V equals half kx squared. So now we are going to equate this and that is half h bar omega, the energy that we have obtained earlier, which is equal to, and total energy is nothing but potential energy. So that's why we are going to equate this energy half kx squared. And here the value of k is nothing but 481. It will be given in the problem. So now x can be easily calculated, which is obtained as 0.0110 nanometer. Last one, this classical limit to length can be compared to the equilibrium bond length by a simple relation, x divided by small x equilibrium. We can convert this one into percentage, so multiplied by 100. And x, just now we have obtained x, which is nothing but 0.110 nanometer divided by this x equilibrium. Already it is given in the problem, so 0.127 nanometer, and that will give us 86.6%. That is the required answer.